This is an explore and reason. So you're really digging into yourself to kind of figure out, what do I know already? And so I'm probably not going to fill in exact answers for what should go here. You should be able to think through and fill this in on your own. We will talk about it, but when we check notes, we will be looking for actual thought. And it's okay if this is not a right or wrong thing necessarily. It's more about, did you try here? Okay, so who knows what figures in the picture are congruent? Yes.
AB, AC, BD, and well, they are congruent, like both figures, I guess.
The whole figures are right congruent. Yeah. Both figures completely congruent. That's what you're saying.
Yep.
And where did you draw that conclusion from?
So the radius and if A is the center point and D is the center point, the radius is going to be the same, no matter.
So both of those are going to be 3 in both pictures, right?
Yes.
Perfect.
Yeah, and then if 2 sides are the same, then the third one has to be,
So only because these angles are congruent, right? Because we got side angle side.
Yeah.
Okay, so then EF is what?
Is congruent to BC.
Right, so what does it equal?
5.27.
Sweet. We're going to roll right along here, and I like to highlight definitions, so I'm highlighting right there. A chord is a segment whose endpoints are on a circle. A segment whose endpoints are on a circle. A segment whose endpoints are on a circle. Okay, we're going to look at example 1, and it's asking us why RS is congruent to UT. So basically, we're going to prove why that is true. First things first, what can you tell me about angle RQS and angle UQT? They are the same, so they're congruent. Why are they congruent? Yes?
Because they're opposites.
Okay, what do we call that when they intersect like that? I think what you're saying is correct. They're across from each other, right? They're opposite of each other. But what's the theorem for that? There we go. I knew if I started, somebody would get there. Vertical angles theorem. So those are vertical angles. We got that. And then we could say that QS, and what can you tell me about QS and QR and QT and QU? What are those? Okay, and so they're all radii, so they're all congruent. So now that tells me that triangle SQR and triangle TQU, what about those? They are congruent, thank you. And how do I know? What theorem do I know based on that information?
Side angle side.
Thank you. So that's our side angle side congruency theorem. And then if the 2 triangles are congruent, RS will be congruent to UT. Who knows my reason? The triangles are congruent. What do we know about their pieces? They're also congruent. Anybody remember how that goes? C, P, C, T, C. All right, take a minute and look at the triad. You do not need to write out a formal proof. You could just explain to me with a couple statements why those angles are congruent. All right, I haven't had anybody volunteer, so I'm going to go ahead and just talk about this. All of these are radii. What do we know about them? They're all going to be congruent, right? So the triangles are congruent by side, side, side. And that means that angle BAC will be congruent to angle DAE by CPCTC. If you wrote something else, but it basically means the same thing, awesome. You did not need to write out anything exact here, but you did need to write something for that triad. And of course, I'm going to highlight, we have another theorem. I want to blow this up without pushing it clear off the page. There we go. All right, if two chords in a circle are congruent, then their central angles are congruent. If two chords in a circle are congruent, then their central angles are congruent. So that means if MN is congruent to PQ, and we're talking about those chords, then we know that angle MTN is going to be congruent to angle QTP Okay, we're going to have a few little challenges in our notes today as we go through. For the sake of time, you do have on the next page the converse. And I'm going to leave that for you to fill in. We will be checking to see if you filled these in on your notes. But if the regular one says if the chords are congruent, then the central angles are congruent, what will the converse say? If the central angles are congruent, then the chords are congruent, right? Remember, it swaps. The converse just switches the order. Okay, so fill that one in on your own. I will fill this in for the completed notes that I post, but I'm not going to take time to fill it in right now. We are going to jump to the next theorem to plug in. And this is the arcs and chords theorem. Chords theorem, where are you? Oh, there we are. Okay, if two arcs in a circle are congruent, then their chords are congruent. If two arcs are congruent, you can use the symbol if you want, then their chords are congruent. Okay. This is where it's really important to be careful in our writing because we're talking about arc, MN, being congruent to arc, PQ, So we're talking about an arc over the top of those instead of a line. And then we can say that MN is congruent to PQ with a line over the top because those are line segments. Those chords are segments, okay? So MN is congruent to PQ. Again, we have a converse theorem that you're going to fill in on your own. We said if the arcs are congruent, then the chords are congruent. So our converse would be if the chords are congruent, then the arcs are congruent, right? We go back and forth. Okay, there is a little typo here. This should say example 2. It is not example 3, it is example 2. Okay. And we're gonna do just a really informal proof here rather than an actual like 2-column official proof. Let's go ahead and mark the stuff that we know. And we know that arc AB, so that's this outside arc piece, is congruent to arc CD. Okay. And we're trying to prove that the segments are congruent. So we're basically going to take that theorem that we just wrote and show where it came from. We're going to prove the theorem. So after we've done this, you won't have to do it over and over again because we're going to just know that if the arcs are congruent, then the segments are congruent. But we're going to prove this. The easiest thing for me to add here would be some radii, right? And why would radii be helpful? What do we know about all of those?
If the central angle is well, they're all congruent.
They're all going to be, all these are going to be congruent. Is that Aaron who said that? Thank you, Aaron. Okay, so we basically know that all the radii from the same circle are congruent, right? And then, Aaron, you actually started to say something about our central angles.
Yeah, if the central angle is congruent, then the chord has to be congruent.
Okay, we did learn that. I want you to go back to what we learned like a couple of lessons ago. What do we know about the measure of the arc and the measure of the central angle?
They're also congruent.
Yeah, they're totally congruent, right? So if these two pieces right here are congruent, then these are also going to be congruent, right? So we're going to just say that angle APB is congruent to angle CPD. And we're going to say that we use some substitution and our knowledge of central angles here, right? And normally in an official proof, we would have like 4 or 5 steps to say that officially. But all I want to do is show you where it came from. So as long as everybody's following that, we won't write out a whole big old proof, okay? But now I have enough information to say that triangle APB is congruent to triangle CPD. And how do I know that? Side angle side congruency theorem. And then if the triangles are congruent, then what do I know about the pieces? And why do I know that? CPCTC. And it is your lucky day. We are not going to do this, try it. So going to skip the try it for that. And we are going to roll right along to the real example 3. But got some theorems to plug in here. Okay, if chords are equidistant from the center, then they are congruent. If chords are equidistant from the center, then they are congruent. If chords are equidistant from the center, then they are congruent. So according to this picture, FS is congruent to ES, and therefore we know that AB is congruent to CD. And as you might guess, I'm going to leave the converse as a challenge for you to fill in. So it will just say if the chords are congruent, then they're equidistant from the center. Okay? This reverses the order of what we're saying. Example 3. Again, we're going to go really informal in proving this. We're just going to say that we have all this given information, that this is perpendicular, which means this is also 90 degrees, and this is 90 degrees, and that's 90 degrees. The other thing that they told us is that PE is congruent to FP. So this part right here, we're going to mark on here and here. Can anyone guess what I might be adding next to this circle to help me prove things? This fits? Oh, I'm going to add some radii. Those lovely automatically congruent pieces. All of those pieces are going to be congruent, right? Because all radii of the same circle are congruent. Okay, now there are 4 right triangles. Looking at the 4 right triangles, not just the 2 bigger triangles, but the 4 right triangles that we have here, can we prove that those are congruent? We can. Who knows how? So looking at this, I know a leg and I know a hypotenuse of every one of those 4 right triangles. So if I know a hypotenuse and I know a leg, we have the hypotenuse leg congruency theorem, right? You might have forgotten that. But you'll notice as we move through geometry, we just keep bringing it back. Okay, so if they're all congruent, then we know that all of their parts are going to be congruent by CP, right? So we're going to be able to say that this part and this part are congruent, and this part and this part are congruent. So AE plus BE is actually going to be equal to CF plus DF, right? Which means that this is the whole side right here, and this is the whole side right there. And so really we've proven that AB is congruent to CB. Okay, super unofficial. Where did that thing come from? We don't have to do this every single time because now we have that theorem that we just wrote down that says if the chords are equidistant from the center, then they are congruent. We just know that. Lucky day, we're going to skip that, try it.
So normally for a question like that, would you just put that theorem or would you have to do all these steps?
You would only just have to say, oh, those are equidistant. So you would just use the theorem. You would just say chords equidistant. And that would be enough. You wouldn't have to go through this whole process. They're showing you where it came from. So that you now understand what it is and have it proven. Okay, this is where we are going to switch to using our compass and straight edge. And in the completed notes, I'm going to go ahead and give you guys some step-by-step written instructions on how to do this. So if you need to know again later, you can go back and look at that if you want. For now, we're just going to work through this. You're going to add Q. Really any point out here, we're going to call it Q. And then we're going to open our compass to the width of the radius. Open your compass to the width of the radius. Okay. And again, if you don't have your compass today, when you can get home, you can go ahead and fill this in. We're going to go ahead and put it on Q and make an arc. Then we move to the next intercept and put an arc. Move to the next intercept, put an arc. Moving to the next intercept, we put another arc. And then from that intersection, we put another arc. And then it should come out, if you were precise in your drawing, it should come out to be 1, 2, 3, 4, 5, 6 points on the circle. 1, 2, 3, 4, 5, 6 points on the circle. And then you just connect those points. Around the edge. And the more precise you were in using your compass, the more precise that this hexagon will be. And we know that because it's a regular hexagon, all angles congruent and all sides congruent, right? That's what the definition of a regular polygon is. Okay. How we can draw an equilateral triangle. This circle is not the same size as the other circle, but we're going to follow the same process here. So we're going to open it to the width of the radii. And again, if you keep your compass there, we're going to put on 1, 2, 3, 4, 5, and then it should come back to the Q being the 6th one. But a triangle only has 3, right? So pick any 3 of those intersection points that are every other one. You could do it in a different place than I did. And then you connect those points. I am, and I'll show you in blue in just a second what it would look like if you chose different 3 points. You could have chosen this one, and this one. And you would have had this one, and this one. Either way, you would have drawn an equilateral triangle. Oops, I was not very precise in drawing my line. All right, part C, we are going to draw a square. We're going to start by drawing a diameter. So we're going to go through the center of the circle. We're going to do that whole perpendicular bisector thing that we've learned earlier in the year. So we open it more than halfway, and we're going to put a mark. And then we'll turn it around to the other side. Put our marks. Oops. And again, the more precise you are in your drawing, the more, or in your constructing, the more precise your picture will be. Go across there. Those 4 points of intersection, divide this triangle into or this circle into 4 equal parts, and we will connect our dots, and we will have drawn a square. Awesome. Okay. We have our next theorem, which is the diameter perpendicular to a chord theorem. And it says, if diameter is perpendicular to a chord, then it bisects the chord. If a diameter is perpendicular to a chord, then it bisects the chord. So if CD is a diameter and AB is perpendicular to CD, then AE is congruent to BE. So those pieces right there are congruent. Our next theorem is the converse of that. So again, we're going to throw that on you to do that converse on your own. You can always come back and check to make sure you wrote it correctly when I post the finalized copy of the notes. One more theorem for today. Says that the perpendicular bisector of a chord contains the center of a circle. Okay, the perpendicular bisector. So we have the perpendicular bisector of a chord. We cut it in half. Perpendicular, that means that S is on CD. That will be the diameter going through there. We have time to look at example 5. Example 5 says an engineer is designing a service tunnel to accommodate 2 trucks simultaneously. If the tunnel can accommodate a width of 18 feet, what is the greatest height that the tunnel can accommodate? And then it tells us to subtract 0.5 feet to account for fluctuations in pavement. We would not want to build this to exact and then have a truck get stuck because there's a fluctuation. Okay, so I'm actually going to redraw myself a circle because they're saying really, even though this is the road right here, we really have a circle that we can deal with here in the tunnel. Okay, so let's redraw ourselves a circle. And if you have a compass and you want to draw a perfect circle, you can do that. I know that my diameter is 27 feet. That's given to me here. I know the width of those trucks is 18. So I'm going to actually draw this piece on, and I'm going to cut it in half because That 18, we're going to call it 9 and 9. Okay, and then I do know that there would be a center here and that radius, if the diameter equals 27, then my radius is going to equal 13.5. Okay, I need to know this part right here. And I need to, I'm going to know that this whole section from here to there is 13.5 because that's a radius, right? But we've also cut this off down here. And this part is 6. So this part is 7.5. So we're looking for x. This is what we need to know so that we can know the total height range. Well, that's a right triangle. And I know somebody earlier said that if I have a right triangle, I can use what theorem? Pythagorean theorem, right? Because I got this right triangle. So I know that 9 squared plus x squared will equal 13.5 squared. And you could figure this 13.5 squared out and the 9 squared out. But for now, I'm just going to say we would subtract the 9, whatever 9 squared is from both sides. And then to get x alone, we would take the square root of both sides. When we plug that into our calculator, we're going to get about 10.06. So x is about 10.06. Now I've got the 7.5 plus the 10.6. We're going to subtract that 0.05 feet to account for this. I guess I didn't even write feet right there. 0.06. And that should come out to be 17.06. Okay, so that is the greatest height. Oh, I spelled height wrong. Sometimes my dyslexic brain is hard. It is 17.06 feet. All right, extra credit will be if you did that, try it on your own. You do not have to do this, try it for number 5. If you do complete the try it for number 5, then you will get some extra credit.